Let's clarify the requirements for service conductor ampacity as outlined in the National Electrical Code, specifically focusing on sections 230.90, 230.31a, and 230.42a. These sections address the sizing of service conductors and their relationship to the service overcurrent protective device. Section 230.90 states that service conductors must have sufficient ampacity to carry the load. This means the conductors must be capable of handling the calculated current demand of the electrical system they serve. However, 230.90 does not explicitly state that the conductor ampacity must be equal to or greater than the rating of the overcurrent device protecting those conductors. In contrast, sections 230.31 and 230.42 provide more specific guidance. Section 230.31a, which pertains to service laterals, mandates that the conductors be sized to have an ampacity not less than the rating of the overcurrent device protecting the conductors. Similarly, section 230.42a, which addresses service entrance conductors, also requires that these conductors have an ampacity not less than the rating of the overcurrent device protecting them. In simpler terms, both 230.31 and 230.42 demand that the ampacity of the service conductors must be equal to or greater than the rating of the overcurrent device. The overcurrent device, typically a circuit breaker or fuse, is designed to protect the conductors from overloads and short circuits. If the conductor ampacity were lower than the overcurrent device rating, the conductors could overheat and potentially cause a fire before the overcurrent device trips. To illustrate this, consider a service entrance with a 200 amp overcurrent protective device. According to 230.42a, the service entrance conductors must have an ampacity of at least 200 amps. Using appropriate ampacity tables found in the NEC, such as Table 310.16, you would select conductors based on their insulation type and the installation conditions to ensure they meet or exceed this 200 amp requirement. It is crucial to understand the difference between the general requirement in 230.90 and the specific requirements in 230.31 and 230.42a. While 230.90 establishes the basic principle of sufficient ampacity, 230.31 and 230.42 provide the concrete rule that the conductor ampacity must not be less than the overcurrent device rating. Therefore, the answer to the question of whether service laterals and service entrance conductors can have a lower ampacity than the rating of the service overcurrent device, provided they are sized to the calculated load, is no. The NEC clearly dictates that the conductor ampacity must be equal to or greater than the overcurrent device rating, regardless of the calculated load, when considering 230.31 and 230.42a. Let's delve deeper into the implications of these code sections. The calculated load represents the expected maximum current draw of all the connected electrical devices and appliances. This calculation is performed according to specific NEC guidelines to ensure the service conductors are adequately sized to handle the anticipated demand. However, even if the calculated load is significantly lower than the overcurrent device rating, the conductors must still meet the minimum ampacity requirement set by 230.31 and 230.42a. For example, suppose a dwelling unit has a calculated load of 150 amps. The service is protected by a 200 amp overcurrent device. Even though the calculated load is only 150 amps, the service entrance conductors must still have an ampacity of at least 200 amps, as per 230.42a. This ensures that the conductors are adequately protected against overcurrents and short circuits, regardless of the typical load demand. It is important to note that the overcurrent device is sized to protect the conductors, not necessarily to match the calculated load exactly. The overcurrent device should be selected based on the conductor ampacity, ensuring that it will trip before the conductors are overloaded. The NEC provides specific rules for selecting overcurrent devices based on conductor ampacity, and these rules must be followed to maintain electrical safety. Furthermore, the installation of service conductors must comply with all applicable NEC requirements, including those related to conductor derriting, protection from physical damage, and proper termination. Conductor derriting refers to the reduction in ampacity that may be required under certain conditions, such as when multiple conductors are bundled together or when conductors are installed in high-temperature environments. These derriting factors must be applied to ensure the conductors can safely carry the intended current without overheating. The service conductors must also be adequately protected from physical damage, such as abrasion, impact, or exposure to chemicals. This protection can be achieved through the use of conduit, cable trays, or other approved methods. Proper termination of service conductors is also critical to ensure a reliable and safe electrical connection. The conductors must be securely connected to the service equipment and the overcurrent device, using appropriate connectors and termination methods. Failure to properly terminate conductors can lead to loose connections, overheating, and potential electrical hazards. In summary, the sizing of service conductors and the selection of the service overcurrent protective device are critical aspects of electrical system design. The NEC provides specific guidelines to ensure that these components are properly sized and installed to protect against overloads, short circuits, and other electrical hazards. Sections 230.90, 230.31a, and 230.42 are particularly important in understanding the relationship between conductor ampacity and overcurrent device rating. While 230.90 establishes the general principle of sufficient ampacity, 230.31 and 230.42 provide the definitive rule that conductor ampacity must not be less than the overcurrent device rating. Therefore, service laterals and service entrance conductors cannot have a lower ampacity than the rating of the service overcurrent device protecting them, even if the conductors are sized to the calculated load. It is also important to consult additional NEC sections and tables to ensure that all applicable requirements are met, including those related to conductor derriting, protection from physical damage, and proper termination. This comprehensive approach will help ensure the safety and reliability of the electrical system. Let's consider a few more practical examples to further solidify the understanding of these code requirements. Example 1. A small retail store has a calculated service load of 80 amps. The electrical contractor plans to install a 100 amp service, anticipating future expansion. According to 230.42a, the service entrance conductors must have an ampacity of at least 100 amps, matching the rating of the overcurrent device. Using table 310.16, the contractor would select conductors with an ampacity of 100 amps or greater, considering the conductor type, insulation rating, and installation method. Example 2. A residential dwelling unit is undergoing a service upgrade. The existing service is 100 amps, and the homeowner wants to increase it to 200 amps to accommodate new appliances. The calculated load is 175 amps. In this case, the service entrance conductors must have an ampacity of at least 200 amps, matching the new overcurrent device rating. Again, the contractor would consult table 310.16 to select the appropriate conductors for this application. Example 3. An apartment building has multiple service entrances, each serving individual dwelling units. The service entrance conductors for each unit must comply with 230.42a, ensuring that their ampacity is not less than the rating of the overcurrent device protecting them. In each of these examples, it is crucial to remember that the conductor ampacity must meet or exceed the overcurrent device rating, regardless of the calculated load. This principle is fundamental to ensuring electrical safety and preventing overloads and short circuits. Furthermore, it is important to note that the NEC is a complex and constantly evolving document. Electrical codes and standards are updated regularly to reflect new technologies, safety concerns, and best practices. Therefore, it is essential for electrical contractors, engineers, and inspectors to stay current with the latest code revisions and interpretations. Continuing education, professional development, and participation in industry organizations are all valuable ways to maintain a thorough understanding of the NEC and other relevant codes and standards. In addition to the specific code sections discussed above, there are numerous other factors that can influence the sizing and installation of service conductors. These factors include the ambient temperature, the presence of corrosive environments, the type of raceway used, and the grounding and bonding requirements. Each of these factors must be carefully considered to ensure that the electrical system is safe, reliable, and compliant with all applicable codes and standards. The NEC also provides detailed guidelines for grounding and bonding electrical systems. Grounding refers to the intentional connection of electrical circuits and equipment to the earth, providing a path for fault current to flow back to the source. Bonding refers to the connection of metallic parts of the electrical system to create a low impedance path for fault current. Proper grounding and bonding are essential for minimizing the risk of electric shock and preventing damage to equipment. In conclusion, the sizing of service conductors and the selection of the service overcurrent protective device are critical aspects of electrical system design that must be approached with careful consideration of the NEC and other relevant codes and standards. The rules outlined in 230.90, 230.31a, and 230.42 are fundamental to ensuring that service conductors are adequately protected against overloads and short circuits. By adhering to these requirements and staying current with the latest code revisions, electrical professionals can help ensure the safety and reliability of electrical systems in homes, businesses, and other buildings. The relationship between service conductor ampacity and the rating of the overcurrent device protecting those conductors is a cornerstone of electrical safety. It is crucial to understand and apply these principles correctly to prevent potential hazards and ensure compliance with the National Electrical Code. Remember that the overcurrent device is designed to protect the conductors, and the conductor ampacity must always be equal to or greater than the rating of the overcurrent device. This fundamental rule is essential for maintaining a safe and reliable electrical system. Therefore, the answer to whether service laterals and service entrance conductors can have a lower ampacity than the rating of the service overcurrent device is definitively no. The NEC requires conductor ampacity to meet or exceed the overcurrent device rating to ensure proper protection and prevent overheating or fire hazard. Finally, always consult the latest edition of the NEC and other applicable codes and standards, and seek guidance from qualified electrical professionals when designing or installing electrical systems. This will help ensure that the work is performed safely, correctly, and in compliance with all relevant regulations.